the graphical representation of motion. We are visual animals. We find pictures more effective at communicating ideas compared to words, which is why representing motion using graphs is so useful in our analysis. So what are graphs in our context? A graph is a pictorial representation of the relationship between two quantities. It helps us to visualize how these quantities vary or not vary with respect to each other. But let us set up some assumptions and conventions before we get started on these graphs. The first one, the horizontal axis is used for time. The vertical axis can be used for distance, displacement, speed or velocity. Next, in our convention, we will consider the point to the right of the origin as being in the positive direction. Conversely, proceeding towards the left of the origin will be the negative direction. Up on the vertical axis is positive and down on the vertical axis is negative. So let us look at these graphs case by case. In order to create any graph, we first need to construct a table. This table will contain two pieces of information. On one hand, we will have the various time intervals at which we are measuring the distance of the object of interest from the reference point. And on the other hand, we will have the specific distances from the origin that the object has covered at that moment of time. We notice that each of these times and each of these distances can be paired with each other. The magic happens when we put these pairings together on the graph. If you look at this graph, some things become apparent. First of all, the graph has a slope. It slants upwards. This tells us that the distance between the object and the reference point is increasing with time. Do note, we are not concerned with the direction in which the object is moving with respect to the reference point. Number two, the slope of this graph remains the same everywhere. The question is, how do we calculate the value of the slope? Let us remember, the slope is the ratio of the change in the vertical axis and the change in the corresponding horizontal axis. So let us take any 2 points on the horizontal axis and name them T1 and T2. We consult the table and locate what are the corresponding values of distance for T1 and T2 in that time. The slope of this graph is given as a ratio. On the top we have the difference in distance that is given by S2 minus S1, and on the bottom we have the difference in time that is given by T2 minus T1. The value of this quotient is equal to the slope of the graph. And since we see that the slope actually has an angle with the time axis, this implies that the object is in motion. Also note that the slope does not change. The slope remains the same throughout the interval of measurement. This implies that the distances covered in equal intervals of time remain the same, which means that the object is in uniform motion. We can now proceed to the next case where the object is in non-uniform motion. Again, we construct a table. On one side, we have the various times of interval measurement, and on the other hand, we have the corresponding distances for these times. Again, we make the pairings. Again, we put these pairings on the graph, and we notice something interesting. The first salient point is that the slope of this graph is no longer constant. As you can see, the slope changes as we proceed from the origin, that is 0, to the end. The slope is actually increasing with respect to time. This implies that the speed of the object is also changing with respect to time, which means we are dealing with accelerated motion. Having seen the graphs for the motion of an object at uniform and non-uniform speed, we shall now observe the graphs for uniform and non-uniform velocity. it is important to remember that when we discuss velocity graphs, the direction of travel must remain constant. A change in the slope of the graph can imply one or two or both things. That is, the speed of the object is changing, the direction of the object is changing, or the speed and direction of the object are both changing with respect to time. So let us see a simple case, the velocity time graph for an object traveling at constant velocity. In order to construct this graph, again we construct a table. In this table, we have the velocities of the object at various times on one side and the corresponding time at which these measurements were made on the other. Again, we form pairings of the times and respective velocities. Again, we put these pairings on the graph where velocity is on the vertical axis and time is on the horizontal axis. We observe some key things here. Number one, we see that the graph is flat in the sense that it is parallel to the time axis. And this is understandable when we notice that the velocity of this object remains the same with respect to time. It does not matter at what time we measure the velocity, the value of velocity remains the same. As a result, the line that we form by joining all of these points together is parallel to the x-axis, or in this case, the time axis. The area under this graph, that is the area of the rectangle, will give us the total displacement of the object in this time interval. Moving on, we can also observe the graph for an object moving in a uniformly accelerated way. In this case also, we will assume that the direction of the object is not changing, but the speed is changing. But the speed is changing at a uniform rate. Again, we will check the times. Again, we will measure the speed at various points of time and construct a new graph. And we observe that in this case, the graph does have a slope. It is no longer parallel with the time axis. And the reason is that at various times from the origin, the speed of the object, the velocity of the object is changing. Another important thing to notice is it does not matter what interval we use, the slope remains constant. This means that for all intervals of time, the rate of change of velocity remains constant. So even though this is a case of non-uniform velocity, it is a case of uniform acceleration, because the ratio of the change in the vertical, which is velocity, to the change in the horizontal, which is time, remains constant. So this graph is an example of uniformly accelerated motion. For the sake of completeness, we will consider one final case, which is the case of non-uniform velocity and acceleration. If you observe the graph adjoining, you will notice many things. First of all, the slope of the graph is not constant, but more importantly, the slope is actually reversing in some places. For example, in the first interval of interest, that is interval t1, you will notice that the slope is positive. It is increasing with respect to time. But then the slope reverses itself. Over the interval t1 to t2, the slope is now negative. It is decreasing with respect to time. And this increase in slope and decrease in slope and the reversal of the slope happens again and again and again. The cases where we see a positive slope are cases of positive acceleration. What this means is, in any interval where the slope has a positive value, the velocity and speed of the object are increasing over that interval. Anywhere where the slope has a negative value, the velocity and speed of the object are decreasing over that interval. This implies that just like velocity, acceleration can also have a zero, positive or negative value. Most of the cases of motion that we see in daily life, for example, the motion of an insect on a floor or the motion of a car or a scooter on a busy road, will correspond to this type of graph, a graph which displays non-uniform acceleration and non-uniform velocity.